Using an oscilloscope is a great first step in any circuit diagnosis. But do you know the difference between a good trace and a bad one? In this video, we'll look at traces from position sensor inputs to the ECM. We'll learn the best setup for an oscilloscope and how to interpret the waveform. Multimeters perform reasonable circuit checks, but react too slowly to display accurate data. An oscilloscope displays electrical signals as a waveform. They have variable voltage scales, adjustable timeframes, and multiple sample rates. This helps paint a real-time picture for the technician. With all that said, let's jump in and have a look at some position sensor waveforms. The TPS can be a contact or contactless type, with the possibility of one or two position sensors. Connect the sample channel to the signal return of the TPS and the ground lead to a known earth point. I'll set the scope time base to 1 second intervals and a voltage scale at a maximum of 10 volts DC. With the ignition on, slowly depress the pedal and watch the display. This is a good trace. We can see the voltage increase and decrease without any abnormalities. It's a great idea to connect a second channel to observe the interaction of both position sensors. This is a good trace of both throttle position sensors working together. An open or excess resistance in the sensor may reflect a waveform like this. During the throttle sweep, the voltage drops to 0, then increases after it passes the fault on the carbon strip. If there was a shorter voltage, the signal will be held at a constant voltage. If there was a shorter ground, the trace may appear like this. The voltage is held at 0. Like the TPS, the APP also houses two position sensors. It's available in contact and contactless. And they both share the same method of voltage measurement. Connection is also similar. Attach one probe to each signal circuit and the ground to a known earth point. As we're working at the pedal, it's a good idea to use pins 4 and 5 of the DLC for the ground, rather than a rusty check strap. Some base settings of around 5 to 10 volts DC and a time frame of about 1 to 2 seconds is great for measuring an APP. Press and release the accelerator pedal while watching the trace. We can see both increase and decrease with no abnormalities. If there was no signal displayed, the fault may be the pedal sensor itself. In this trace, we can see the pattern intermittently drop out and then resume again. This may be caused by an open or excess resistance within the sensor. It's a good idea to backprobe both signal terminals at the ECM, as this can show any faults within the harness. A short to ground in the signal circuit would look like this. The voltage is held at 0. If the voltage remained high, there may be a short to voltage. Like the TPS and the APP, the EGR uses the same method of position sensing, either contact or contactless. The best way to test an EGR sensor is using a scan tool to actuate the valve and monitor the signal return on the scope. Attach one probe to the signal circuit and the ground to a known earth point. Some values would include a time base of 1 to 2 seconds and a voltage scale of around 5 to 10 volts DC. Command the EGR valve to open and close with the scan tool. In this trace, we can see the position is held open, then as it closes, we can even see the pintle bounce. This is a good trace. If the voltage was constant, this may indicate a shorter voltage. If the voltage displayed 0, this may indicate a shorter ground. In this section of the trace, we can see the waveform has jagged edges and changes shape. The voltage may also be reduced. This could be the result of an open or excess resistance. There are two common types of cam position sensors in use today, digital and analog. They use the same method for connecting to the scope, but the voltage and timescales differ. An inductive type requires a time base of around 20 milliseconds and a voltage scale of plus or minus 5 volts. For the digital, a voltage range of 5 to 10 volts DC and a time base of around 50 milliseconds is used. Here is a sample of a good digital cam position sensor. In a digital sensor, depending on the severity of the air gap, there may be little to no display. In this example, the signal drops intermittently to 0. An open or excess resistance may appear to look like this. The tops are jagged or parts of the trace may be missing. A shorter voltage in the signal circuit will display a constant voltage. A short to ground will present a signal held to 0 volts. A missing pulse in the waveform could be the result of a damaged reluctor wheel or excess resistance in the circuit. It would appear like this. Back EMF from the fuel injector closing can be seen in this section of the trace. This isn't a fault, but it's common on GDI and CRD vehicles. Here is a good sample of an analog camshaft position sensor at idle. The peaks are clean with no interference. They cycle from -1 to +1 of a volt. An open or excess resistance fault will change the shape and frequency of the waveform, depending on the level of resistance. A shorter voltage or ground in this circuit will present the same waveforms as the digital sensor. An excessive air gap between the sensor and the reluctor will cause the amplitude of the signal to be reduced, or there will be no trace at all. The crank angle sensor is used to locate top dead center cylinder number 1. Like the cam sensor, it's available in digital and analog. Again, attach one lead to the signal terminal and the other lead to a known ground. A scale of 20 volts DC and a time base of around 5 milliseconds should provide an acceptable trace. Monitor the display. Here we can see multiple on and off peaks, followed by a large gap. This is known as top dead center. This is a good trace. We can tell this by the even gaps in the reluctor and no rounded sections. Resistance in this trace will cause the reading to be jagged or missing teeth. A possible shorter ground in this circuit will display 0 volts. A shorter voltage will keep the voltage at a constant high. An excess air gap can cause the peaks to be smaller and even cause there to be no signal. The ideal setup values to use for an inductive sensor would be a voltage scale of 20 and a time base of 10 milliseconds. For the best connection, backprobe both signal terminals with the sample and ground leads. Top dead center is displayed in this part of the trace. It's indicated by the gap in the frequency wave and the spike in amplitude. A shorter voltage here will result in a constant voltage reading with no trace fluctuation. A shorter ground may appear with no trace output and a 0 voltage signal. Excess resistance in the circuit will reduce the amplitude of the trace and will look like this. An excessive air gap between the sensor and reluctor will reduce the amplitude and frequency, or may even result in signal loss. Today, there are two sensors employed to measure rotational speed. One is digital and the other one's inductive. To connect to the digital sensor, backprobe the signal side of the connector and attach the negative lead to ground. Set the scope with a scale of 20 volts and a time base of around 2 milliseconds. Here is a good example of a wheel speed trace. Note the waveform is clean with no rounded sections. In this trace, we can see the amplitude is reduced and the frequency intermittently drops. This may be the result of an open or excess resistance. A shorter voltage in this circuit will see the waveform held at a constant voltage. A short to ground within the circuit will cause the voltage to remain at zero. An excessive air gap between a digital sensor and the multi-pole ring will result in the signal voltage to be lower than expected, or it may even be missing. The inductive type produces an analog signal. Connect the sample and ground leads directly to the sensor. Be aware that it should be disconnected for this test. Set the scope to 1 volt with a time base of 200 milliseconds. Spin the wheel by hand and watch the trace. This is a good example of an inductive waveform. A shorter voltage will be displayed as a constant voltage on the screen. If there was a shorter ground in an inductive system, the trace will remain at zero. An open or excess resistance here may reveal a reduction in the amplitude or even sections missing from the waveform. When you get a chance, play with the scope. Get familiar with the setup and the sensor patterns. Continuous training is the key to your success. Thanks for watching. See you soon.